the mission, soon to be formally known as GEMS, because we have to change our name at some point. Haven't bitten that bullet yet. But it's a discovery mission to understand terrestrial planet evolution, and it happens to be going to Mars. So what GEMS is, it's a single lander going to Mars to do geophysical measurements. We've got a very small number of science goals and objectives that will inform a lot of science. We want to understand the formation and evolution of terrestrial planets, and to do that, we're going to look at the basic structure of the Martian interior. Most people don't realize that we have really very little idea of the thickness of the crust, the size of the core, the structure of the mantle on Mars, and even less idea of what you can do with those kinds of things. But we're going to measure that with a single lander on Mars. Why is interior structure important? It turns out that by understanding various things about the basic building blocks of the interior structure, we can inform our knowledge of how these planets formed, how they got to be where they are today, how they went from sort of a homogeneous mass of chondritic material into the very complex things that we walk around on. Things like crustal thickness, it's a very sensitive indicator of the early thermal evolution of the planet. The core tells us very much about how the planet formed early on, how the elements of the planet separated from each other and differentiated into the planets we know. Mantle composition dynamics is key to many surface processes that we see on the planet today and many processes that happened early on. And we can put all these things together to constrain our models, which are very speculative at this point, as to how the planet evolved. Why Mars is particularly a good place to go, we don't have this kind of information for the Earth anymore, at least not in understandable form to a large extent, because the vigorous mantle convection, plate tectonics has stirred everything up, and we don't really have the structures that reflect the initial differentiation. But on Mars, we have evidence from SNC meteorites, from dating of surfaces, that a lot of these things probably still exist on Mars, almost certainly still exist on Mars, and we can use that to our advantage. So we think that measurements of the Martian interior will really reveal structures that still reflect the initial processes, the initial differentiation of planetary formation. I like to talk about GEMS as a terrestrial planets mission that just happens to be going to Mars. Mars is sort of in the sweet spot. It's big enough to actually have undergone all the processes, or most of the processes that are important for terrestrial planet evolution, but it's small enough or inactive enough to have sort of frozen all this stuff in over the last 4.5 billion years to still have that information readily available to us. So kind of a basic project overview. GEMS is a JPL managed mission. It's a Lockheed Martin spacecraft, and we share operations. The instruments are contributed by our partners in Europe. It's a late March 2016 launch, about a 6.5-month trajectory to Mars, direct entry. We have a very intensive month to deploy the instruments, get the spacecraft and the science systems working, and then we sort of turn off the one way of the radio for the science team and just collect data for the next 2 years at very low cost. I think I like to emphasize that this is an international mission. It's really an international science team. More than half the science team comes from other countries. My management usually tells me not to emphasize this, that it's a bad thing that we're doing all this science for Europeans and the Japanese, et cetera, et cetera. But I see this as a real strong point for our mission. We didn't bring these people on board just to have any kind of balance or anything like this. We really went out, got the best scientists, the best instruments in the world to do this job, and we didn't have to limit it to just one country or one institution. We really have cast a wide net, and I think we have an amazing science team. I won't go into this in any detail, but suffice it to say that Conventional geophysical measurements usually assume that you have a network of observatories on the surface, and this is what we've been working for the last 20 years to get to Mars with marked unsuccess. But by using some state-of-the-art analysis techniques, we can now use a single geophysical station to get a lot of the information that was initially thought to be only available by network analysis. And so by using these analysis techniques, by using sort of unconventional seismic sources such as impacts, such as tidal excitation by Phobos, we can get the kind of information that we need to do this science. The payload consists of only 2 instruments, a seismometer and a heat flow probe, although we have 3 investigations because we can use the radio tracking system to get rotation data for Mars. And if you go down the line, we actually have 4 payload elements because in order to use the seismometer and the heat flow probe, they actually have to make it that last 70 centimeters from the top of the deck of the spacecraft down to the ground. So we actually have 2 landing processes, one that gets us from the Earth down to within 70 centimeters, and then we have another process that gets us that last 70 centimeters, the one that Viking forgot to do. So we have the 2 instruments, plus we have an instrument deployment arm and a camera on that arm, which is used to do our landing site certification once we get down for that few square meters that we can put these instruments within. And this payload, as I said, it's a small payload, but it's actually all in hardware that exists today, albeit in some cases not quite the same configuration that we will fly. But these are instruments that have been developed over a fairly long period of time and at a fairly high degree of development. The spacecraft also is another one that's been flown before. Our intention is to fly the Phoenix spacecraft as close as humanly possible to what was flown before, both in terms of the hardware, in terms of the people who will be building it and operating it, and the relationships between JPL and Lockheed Martin. And so we plan to make this as close to a build-to-print and fly-to-print as we could possibly can. Mission design overview. A JPL presentation always has to have a chart like this with little circles and things. But you can look in the presentation if you care about these kinds of numbers. And this EDL chart here has probably been used in almost every mission since Pathfinder with minor modifications. So the entry, descent, and landing is something that's been done before. We think we know how to do it pretty well now, and we're going to try to do it just the way we've done it before. So in summary, I think we've got some awesome science. It's not just Mars. It applies to big picture questions for the entire solar system and other solar systems as far as that's concerned, plus a lot of cool Mars science as well. Our goal is to keep this at low risk, both in terms of technical and cost risk. We do this by keeping a focused payload, by having relationships and hardware that we know before, and we intend to achieve this by ruthless adherence. I like this word ruthless. I put that in my proposal to heritage and established capabilities. So we intend no improvements to the spacecraft capabilities as flown, no augmentation of the science past what we put in our proposal, and no science interactivity on the ground once we start our surface operations. So that's it.